Alright, welcome back. Now, on this slide, I actually kind of made a mistake here. I didn't mean, I was rearranging slides. I didn't mean to highlight the fourth one there, paleoproxies. We've already talked about this challenge of how do we know what the atmosphere did in the past. And we've learned that, well, it kind of depends on what you mean by in the past. I mean, if you only need the last few decades, satellite data is going to be great. If you need only the last, several decades to a few centuries, the instrumentation record is going to be great. But we need some other ways to obtain meteorological or climate information from farther back. And that's where our third and fourth choices are there, the historical records and the paleoproxies. Both historical records and paleoproxies are an example of what we call proxy records. Human activity results in records that have information about climate in them. We're going to see examples of where humans record river heights or harvests and so on, and that has climate information in it. Or there's the natural world, and things that happen in the natural world can contain signs about the climate of the past. Both of these are examples of proxy records. I mean, nobody was planning for these harvest records to contain climate information. It just worked out that way. The natural world wasn't deliberately putting certain isotopes of oxygen into the shells of marine creatures. It's just how it worked out. But those ratios of those different isotopes of oxygen are going to have climate information in them. So the human records are going to provide what we call the historical record, whereas the natural world, the word for that kind of information is that it's a paleoproxy. Paleo is kind of a word that means something like old. Okay, so these are the oldest of the records here. But either way, they're a proxy. Now that word proxy can be a tricky one. I mean, here's a Google definition card for proxy. It says the authority to represent someone else, especially in voting. I don't really care for that definition very much. A figure that can be used to represent the value of something else in a calculation. I like that definition better. These are going to be pieces of information we can use to kind of represent the temperature of a region or the precipitation of a region or so on. And a classic example of a human data archive, that a historical data archive that contains climate information, is the missionaries to South America. Spanish and Portuguese missionaries reached South America really shockingly soon after Christopher Columbus's voyages, and they set up missions and villages and so on, and started raising food, in particular gourds and things like that, and pumpkins and so on, and, whatever was good or whatever was bad about that, one of the things the missionaries did great was maintain records about their crops. And these records about how many grapes they got this year off of this vineyard, or how many pumpkins they got, or how much maize they raised, or whatever, go back to literally the early 1500s. In 1492, Columbus sailed the ocean blue, and by the early 1500s, we've got missionaries in Peru. Okay, there are records surprisingly far back. And that's actually really interesting from a climate perspective, because the parts of the world the missionaries happen to be, namely certain areas of Western South America and so on, have weather and climate that is very directly related to El Nino. Now remember, El Nino is this global weather phenomenon that happens about every 4 to 5 years or something like that, and we have a lot of anxiety about the possibilities that El Nino might be changing over time. Maybe it's getting stronger, maybe the events are happening more often, maybe they're happening less often, who knows? But all that would have a very large impact on us, and we need to know about that. Well, this is pretty amazing, because we have information about the strength of El Nino from these missionaries. Not because they were measuring sea surface temperature gradients across the tropical Pacific. No, they were counting gourds, or pumpkins, or grapes, baskets of grapes or whatever. But by recording these crop yields, the missionaries provide a historical proxy for something like rainfall and temperature and so on in lots of different places in South America. And there were a lot of these missionaries out there in Peru, what became Peru and Ecuador and Bolivia and so on, in places that are very sensitive to the weather associated with El Nino. So this helps climate scientists understand if the strength or the frequency of El Nino is changing. And I can tell you, by the way, from those records, we believe that in general it is not, at least not prior to the Industrial Revolution. But in the roughly 500 years of record we have prior to that, it seems like the processes of El Nino have been relatively stationary. They've had approximately the same period, approximately the same strength. Now there's questions about, like, since the 1970s or something, but that's not where we can go with records of pumpkins from Peru. Another example of a historical record that comes to us as a way that we can glean climate information from something humans were doing comes from an instrument called the Nile Meter. The Nile Meter is an Egyptian technology. This actually got started all the way back in, like, if you're thinking Egyptians as in, like, pharaohs. Okay, so we're talking, like hundreds of years BC, maybe even thousands of years BC. The Egyptians were very, very invested in knowing about the height of the Nile at any given time. You might remember, I mean, the Egyptians lived in a very narrow strip of land right along the Nile River, and the annual flood of the Nile River pretty much provided the irrigation for their crops, which was their source of food. So the height of the Nile was something they cared very much about. And there were a handful of these stations called nilometers. I doubt that was the word in their language, sounds wrong, but that actually it was this long shaft and that would fill with water, and there were marks along a pole that went through the shaft, and based on the height of the river they could examine and record how high up and down that shaft the water was. And this records, well, in a piecemeal way, exist back for thousands of years, but starting at the beginning of the Islamic era, Muslim scientists were amazing about these kind of records and so on. So starting in like the 7th century AD, we have these records that are really quite high quality to the height of the, very systematic, and they provide information about inhomogeneities in the data and so on. So we have very good information about how high the Nile was at a lot of times in the past. Now, that turns out to be a really good paleoproxy, because the height of the Nile is actually determined, I mean, there's no rainfall in Egypt to speak of. The height of the Nile is not about runoff in Cairo and Alexandria and so on. The height of the Nile comes from a large watershed upstream from Egypt in like South Sudan, Ethiopia, Kenya, Tanzania, and so on. A very large part of equatorial East Africa forms the headwaters of the Nile. So the height of the Nile is actually a proxy for total rainfall over this very large area. And total rainfall over that large area has all kinds of climate information about it. I mean, we could be learning about things like the strength and timing of the monsoon, the strength of El Nino. El Nino has consequences for rain in that part of the world and so on. So suddenly, I mean, there's all kinds of climate information we can glean just by knowing how great the flood was on the Nile at any given year. That's really smart. So these kinds of historical records go fairly far back. I mean, there's all kinds of climate parameters we can derive or at least estimate based on historical records, and those historical records can go back many centuries. And depending on exactly how worried we are about, like, the absolute values and so on, sometimes even thousands of years. But in the long run, there's going to be all kinds of data homogeneity problems if we're working with historical data over those kinds of time periods. The ancient Egyptian nilometers were a good idea, but they were not as systematic as the nilometers that were constructed in Egypt during the Islamic era. So we have a data inhomogeneity problem there. If we want to try to be more systematic about this, we're going to need to use natural paleoproxies. And these paleoproxies are going to be long-lived chemical or biological systems that have the climate signature imprinted upon them. Oh, that's jargon that came from some textbook. What are we talking about? The best way to talk about this is to just show an example of a paleoproxy, where there's a chemical signal in the system that tells us something about what the climate was doing. And the best example is ice sheets and ice cores that we dig out of ice sheets and glaciers and so on. I mean, the ice in a glacier or an ice sheet provides all kinds of useful information that has climate data hidden in it, dating back to the time when the ice fell in the form of snow on the top of the ice sheet or the top of the glacier. Now, this is actually something pretty cool that I know a little bit about. Not that I've ever actually done ice cores or something like that, but I have buddies who I went to grad school with who did, and so on, and they've gone on these expeditions and so on. And so here's a fairly typical picture of what the kind of things they do is they have these instruments that can go, this equipment that can go out, and the climate scientists dig these ice cores through ice sheets and glaciers and so on. And we're going to be able to, you'll see how in just a little bit, but we're going to be able to determine the age of the ice that's being pulled out. You can see it's sealed up in like a steel canister here, and then those steel canisters are taken to cold storage facilities at like the Bird Polar Research Center in Columbus, Ohio, or I think the National Snow and Ice Data Center has some too, where they store these cores, and then characteristics of the ice cores, like its chemical composition, get translated into climate information. And it's pretty cool. I mean, you can, like, this is actually an image from an ice core in here, where you can see all these layers and so on. We'll talk about what that all could be in just a moment here. I want to pick this apart, though, into two different things. I mean, I like this business of finding out, like, how things like its chemical composition gives us climate information. But before we do that, let's actually ask ourselves, how the heck are they determining the age of the ice at different heights in this ice core? Well, part of the story is you got to remember how glaciers and ice caps and so on form in the first place. Ice sheets, like the Antarctic ice sheet and the Greenland ice sheet, and glaciers in mountains, form any place where there is more snow falling in the winter than melts during the warm season in the summer. And, well, you know that definition of like a glacier and so on, but, pardon me, but it isn't until you pause and think about it that you realize, oh, that means it pretty much has to form layers like what we're seeing right there. Because, you know, a certain amount of snow will fall on the ice sheet, some of it will melt in the summer, but then more snow will fall on top of that, and you're going to get some kind of annual structure to it. As you start at the top of the glacier, or at the top of the surface of the ice cap, and work your way down, you're encountering older and older ice. So like, let's just say on that diagram up there at the top, off to the left is older, and off to the right is younger ice. There's a structure to this. If you examine it under different, lights or under different chemical techniques or whatever, there's going to be some kind of annual structure. There's going to be clear denotation, markings that indicate each year as this cycle of depositing snow, some of which melts, but not all of which, and then more snow falls on top of it. And that annual structure is in some way revealed. Often it's revealed by the presence of more dust in the ice itself. There'll be, there'll be like, relatively clear ice, relatively dusty, relatively clear, relatively dusty. The dust is often deposited on a glacier in the summer season. I mean, like, here's a fairly typical, this is actually one of those pictures I showed you from my trip to the Canadian Rockies. Well, here's a lovely glacier coming down the side of a mountain or whatever over a period of time. Well, I was there in June. All the seasonal snowfall has already melted back, and this glacier, with potentially thousands of year-old ice, but with relatively fresh ice on the top, right? That's felt this winter. Now it's surrounded by exposed rock and soil and dust and so on. So in the summer, in the warm season, dust is transported just by winds and stuff like that onto the surface of the ice, and then in the cold season, more snow will fall on top of it. So you'll get this local transport of dust onto the surface of the glacier or whatever. And I mean, when I say local, I mean it might be farther away than just like right there, but you get a signal, well, there's dust in it from the warm season. In other environments, there might be other ways in which you can denote the annual structure of the layers. For example, often they do it using the structure of the ice crystals themselves. Ice looks like ice to me, but I'm not, a paleoclimatologist who studies the cryosphere. Under a microscope, they can tell the difference between, for example, ice where it has melted in the warm season and then refroze in the cold season, and you get kind of like layers of crusty and clearer ice and so on. Again, it's a specialization. One goes off to grad school, learns the techniques, uses the instruments and so on. But either way, however it was done, we now have a way to identify, look, this is 1 year's ice. Then this is the next year's ice, and this is the next year's ice in these cores. Do we know the exact year that ice formed? Well, first off, let me ask you, is that even important? I mean, it isn't necessarily the case that I particularly care that one particular little slab of ice in there, oh, that is from the year 7,326 BC. Odds are I don't really care about that. I'm more concerned about, like, this is during the last ice age, and this stretch of it here was as the glaciers were retreating, and this stretch here was during the Holocene climatic optimum. We'll be learning about that term later. I don't really care that that was exactly 7,226 BC. I just need to know roughly where it is, and I can compare like this year to that year and so on. But as long as I just kind of have a vague sense, that's all I really need. But in some cases, yes, we might actually know the exact year. For example, there's often, the scientists will look for evidence of a particular volcano. Okay, we can find volcanic ash at some particular layer in the ice core there, and then say, yes, and we know from records that is, that contains a certain amount of sulfur, and therefore it is from this volcano that erupted in this particular year, and then we can work from that. Oh, I see something interesting happened in this layer of ice over here, and that's 1, 2, 3, 4, 5, 15 years later. Okay, so we now know the exact year of that. So we can sometimes actually find, for example, markers like volcanic ash. Tragically, in the modern times, often they can find like evidence of particular pollutants or strontium-90 from open nuclear testing and things like that in the 40s, and date ice sheets from that way. But now that you know the year of each layer of those ice, or at least know it accurately enough for your purposes, we can start trying to extract climate information from the ice. Now, that could be really simple. That might just be things like you want to know how much ice there was each of those years, which might be a measure, might be telling you something about, for example, the amount of precipitation that fell that year or something like that. That would be a relatively straightforward thing to do. Or they very carefully extract the bubbles of trapped air that are in that ice, and from that little bubbles of trapped air, they can actually determine the chemical composition of the atmosphere at that time. This is where they get information like, for example, what the carbon dioxide concentrations were during the last glacial maximum. Okay, we have ice from the last glacial maximum. It has little trapped pockets of air in them, and we know the rates at which like air molecules diffuse out of a bubble like that, so we know that it is not contaminated by environmental air around it and so on. And from that information, we can actually find out like what the carbon dioxide concentration was in past. I'm always amazed by that. These are just tiny little samples of air trapped in these ice cores, but they can do that. But there are often even more impressive things we can do with this, like we can actually learn about the temperature of the air in the, we can actually learn about the temperature of the oceans. The oceans where the water evaporated that then later fell in the form of snow and became part of that glacier or part of that ice cap. But we'll come back to that. Okay, we're going to come back to that business of getting temperature information. For now, though, let's just talk about what we're getting from this ice core stuff. Now, as it happens, ice cores are a great paleo proxy for climate information going back about 800,000 years, which is a really long time, obviously, but we'd love to go farther back. The problem is we don't actually have ice older than about 800,000 years. 800,000 years is about the cycling time for ice in Antarctica and Greenland and so on. Even the oldest ice there is younger than that. Most of the ice, there's a cycle to it, right? I mean, it gets deposited and then the weight of it pushes those glaciers towards the ocean. At some point they melt. And so we don't actually have ice older than about 800,000 years. But the IPCC AR5 has obviously assessed a lot of this information and tried to figure out what to tell decision makers and policymakers and so on about it. And what we've learned from like the samples of air we get from the little bubbles in the ice is that present-day concentrations of atmospheric greenhouse gases like carbon dioxide, methane, and nitrous oxide exceed the range of concentrations observed in the ice cores during the last 800,000 years. In other words, we have a lot more carbon dioxide, methane, and nitrous oxides in the Earth's atmosphere now than we have in that 800,000 year time frame. Ouch. Now, the current rates of carbon dioxide increase, or methane increase, or nitrous oxide increase are unprecedented due to the highest compared to the highest resolution ice cores of the last 22,000 years. Okay, we have the best records in that last 22,000 year period. Let's be clear about what they're saying there. They're saying not only do we have the most at the present time, we've never seen anything where we are rising that fast. Okay, the increase in carbon dioxide that we are seeing is not typical of other things that have happened, at least in the last 22,000 years. So ice cores are a great example of like a paleo proxy for climate information. They're actually only one of a whole bunch of similar sort of ideas we have out there too. For example, a former Creighton student actually is now a grad student at Columbia University in New York, and there they work using paleoclimate data that comes from ocean sediments. They do a similar sort of thing where they make a core through ocean sediments, and based on the stuff that's accumulating on the bottom of the ocean, like dead microorganisms and stuff like that, they can figure out climate information about the ocean, or about the sediments that were coming in from a river or something like that. They can learn about the environment that those sediments were coming from. And they can do things like, say, hey, I see more of these species than these species. This group of species tends to thrive when the water temperature is greater than this. This group of species thrives when it's less. This gives us climate information. Or often it'll be about the chemistry and isotope ratios in the shells of the microorganisms that are in those sediments. And we'll learn more about that chemistry in just a little bit. Paleoclimate information can be derived from corals. I mean, we tend to think of corals as like this precious environmental resource, and of course it is, but they're also a climate information storehouse. Corals grow at different rates, at different temperatures. They have different species that are thriving in the coral ecosystem at different, and they're constantly growing and making layers. And from those layers, we can resolve things like the annual cycle. We can resolve what temperatures of the water were, what the salinity of the water was, and so on. The minerals that were in the water that were incorporated now into the exoskeletons of the microscopic creatures. We can learn about the isotope ratios in the ocean, which in turn will give us information about the temperatures. All from, drilling through a coral reef. That's great. That's amazing that this kind of stuff can be done. Now notice I keep coming back to that same idea that there's something about oxygen isotope ratios that can tell us something about the chemistry and the temperature of the world at that time. That's where we're going to go now. But before we do that, let's answer three quick questions, okay? Question 3. In some winters, the River Thames in London freezes, and a so-called frost fair is held. Records of when the river froze and how long it froze are an example of blank that provides paleoclimate information. Is this an example of A, an instrumentation record, B, a historical record, or C, a paleoproxy? What is the right word to describe these records of these frost fairs on the River Thames in London? Make a choice from these 3 options and get a little feedback before you move on to question 4.